Section 12.7, heat and temperature change, specific heat capacity. This is focused on solids and liquids. If you want to know the heat that is either supplied or removed in changing the temperature of a substance, it's going to follow this equation. So in order to, once again, change the temperature of a substance, the heat that must be supplied or removed is equal to Q equals mc delta T, where Q here is our heat. It's the symbol we will be continually using for heat. And then M is the mass. C is known as the specific heat capacity, more on in a moment, and delta T is the change in temperature. So specific heat capacity tells you how the material responds when you add heat to it in terms of changing the temperature. Let's look at some examples of it. Before we do, common unit for specific heat capacity is the result of everything else that we just saw there, right? If we solve this for C, we'd get that C is equal to Q divided by everything else, divided by M, divided by delta T. So if we look at the subunits here, Q is an energy flow, so it's in units of joules. M is mass, so that's kilograms. Delta T is in Celsius degrees. And so that's exactly how we get down there to that specific result. All right, so with this in mind, let's take a look at some various specific heat capacities. All right, so here we have specific heat capacities for solids and for liquids. All right, we notice it's in the units that we just found. So we have aluminum's 900, copper's 387. We could jump down to some of the liquids, right? Mercury has a really low specific heat capacity, whereas water has the highest value for the specific heat capacity. What does that mean to have such a large value? Well, one way of looking at it is that if you put in a certain amount of heat Q and you have a large specific heat capacity, you're going to get a pretty small change in temperature. Not going to see a lot of change. If instead you put in some amount of Q, the same amount of heat, but you have a very small specific heat capacity, then more of that heat can change the temperature. And that's one of the reasons why copper can change temperature much faster than glass, for instance, if you've ever used various baking dishes, and also why water takes a lot of energy in order to change the temperature of the water. It also keeps that temperature longer because of that. So let's take and check out an example of how this heat flow can relate to changing the temperature, the specific heat capacity. So this is a modified version of example 9, a hot jogger. 65 kilogram jogger can generate heat at a rate of 16 times 10 to the 5th joules per hour. This heat is removed from the body by a variety of means, including the body's own temperature regulating mechanisms. If the heat were not removed, how much would the body temperature increase after half an hour? All right. So as we're paying attention to this, what does it tell us? Well, notice it gives us our mass, the 65 kilograms. It's going to be the mass. And it also gives us something with joules, but we have to be careful here because it's joules per hour. So, and it does say that's heat, but it's heat at a rate. So that's more of a Q over T is equal to 16 times 10 to the 5th joules per hour. We ultimately want to find how the temperature will increase. So that sounds like a delta T. And they give us a time, right, after half an hour. Cool. So now that we know the time, we're able to convert this Q over T into just a Q, and that would be heat. So we know the amount of heat going in, we know the mass, the jogger. Can we figure out the delta T? I think we can if we know the specific heat capacity of the jogger, right? So if we look back at the previous slide, the human body is right in there. I'm gonna clear my drawings. Look, human body, 3,500, great. So because it's a human body, we can take that value and run with it, and we'll be in good shape to solve for delta T. So if we want to find Q, that's once again going to be that 16 times 10 to the fifth joules per hour times half an hour. The hours cancel out, so we get half of 16 is 8 times 10 to the fifth joules. That's our Q. And now we're going to go to the heat supplied or removed in order to change the temperature equation, Q equals mc delta T. And we want to solve for delta T. So we'll divide the mc to the other side. So we have Q divided by mc. So we have our Q, the 8 times 10 to the fifth, divided by 65 kilograms, divided by that specific heat capacity of the body, 3,500 joules per kilogram per Celsius degree. And so that comes out to 3.5 Celsius degrees. So we notice that the joules will cancel out, the kilograms will also cancel out, and we're left with 1 divided by inverse Celsius degrees, which just comes out to Celsius degrees. So 3.5 Celsius degrees doesn't sound like a ton, but if we convert to Fahrenheit, we notice that that's more than 6 degrees Fahrenheit. 6.3 to be exact. So if you have someone who increases their body temperature by that amount, you're going to be running a fever, right? A 104 fever, no less. That person's going to the hospital. So that's part of why the body has a bunch of temperature regulating mechanisms, right? Maybe you can think of some of them. One of them is sweat. That actually helps to remove heat from the body so that you do not overheat. Other animals like cats don't necessarily sweat, but they have other means, right? You might see them pant, and that's their way of removing heat from the body so they do not overheat. So this helps to highlight the importance of those mechanisms to be in place. All right, now this equation was just for solids and liquids. For gases, we're going to see the value of specific heat is going to depend on whether the pressure or the volume is held constant. We're going to come back to this in chapter 15. So you'll have to wait until then to talk about gases. The distinction of constant pressure volume isn't very important for solids, so we're able to move along with that. Another useful thing is some of the other units of heat. So another unit of heat is kcal. This is one that's often associated with energy, like food, right? Your nutrition labels has something with calories with a capital C. Turns out that's equal to the scientific 1 kcal, or 1,000 little c calories. But that's what's associated with internal energy and heat. And it turns out it was a scientist named James Joule who discovered that the energy done in work that was measured in joules was the same as the heat of energy, that you could see some transfers, like if you rubbed your hands together, which is doing work, that can also increase heat, right? So he made that connection that joules and calories were actually just two different ways to describe the same thing, the same quantity of energy. So these are some useful conversion factors that you can use to go back and forth between different energy units. Another important application of specific heat capacity is calorimetry. So if you want to try and understand a particular material, you might want to measure its specific heat capacity, and that can tell you about the material. The common way this is done is by isolating that material so that there are no heat losses to the surrounding. Excuse me. So you can put an unknown material, we'll see an example of this in just a moment, in an isolated calorimetry cup that has a thermometer so you know the temperature of everything going on, right? And you can keep it isolated from the environment. If you're able to truly isolate it from the surroundings so that you don't lose heat to the surroundings, then if you heat up this unknown material, the heat that it loses is going to be equal to the heat gained by everything else, by the calorimetry cup and the liquid like water. This is a key equation that we'll be using in this chapter, that the heat gained is equal to the heat lost. We'll see this in action in just a moment. One note with this equation is this assumes that all the quantities are positive. And in order for all the quantities to be positive, with the change in temperature, we're not going to just do final minus initial, because that will sometimes have a negative change in temperature if you've lost heat. We're going to always do it as the higher temperature minus the lower temperature, and that will get the algebraic signs to work out properly. So keep delta T positive if you want to use this heat gained is equal to heat lost equation, which is a great equation. It's one that I recommend using. Let's check out an example of calorimetry. So example 12, measuring the specific heat capacity. Cool. Calorimeter is made of 0.15 kilograms of aluminum, that's just the cup, and contains 0.20 kilograms of water. Initially, the water in the cup had the same temperature of 18 degrees Celsius. A 0.04 kilogram mass of unknown material is heated to a temperature of 97 degrees Celsius and then added to the water. After thermal equilibrium is reached, the temperature of the water, the cup, and the material is 22 degrees Celsius. Ignoring the small amount of heat gained by the thermometer, find the specific heat capacity of the unknown material. All right, so in approaching this, we want to go back to that heat gained is equal to heat lost equation. So first we want to ask, what is gaining heat here? Well, what's gaining heat is what's going to be increasing in temperature, right? So we notice that everything ends up at 22 degrees Celsius. So what starts out at a lower temperature than 22? Well, notice it says that the water and the cup both have this initial temperature of 18 degrees Celsius. So they are increasing their temperature, they are gaining heat. Versus this unknown material, which we could call a rock, right? The rock starts out at 97 degrees Celsius and goes down to 22. That's a huge loss of heat. The rock is giving off its heat to the surroundings. So now we can plug that in using our Q equals mc delta T equation on the next slide. Let's take a look. So we're going to say heat gained is equal to heat lost. I might even add another line here, that we have the Q of the aluminum cup plus the Q of the water is equal to the Q of the unknown, our rock. This is a more general way, and so I encourage you to write both of these lines because that will really help you set you up for success in the coming sections. So we know that for the aluminum cup, it changes temperature. So we write this as mc delta T for the aluminum. The water also changes temperature, mc delta T for the water. And the unknown rock changes temperature, mc delta T. Now all of these quantities are for the unknown rock, right? This isn't the same mass for all of them, so we can't just divide it out. It's just been written so that they're all on the outside. This aluminum is assumed to apply to each of those individually to save a little bit of space. Now we're trying to solve for the specific heat of this unknown material C. So all we have to do is divide by the m and the delta T of the unknown, and we have our equation set to go, right? So we have the mass of the cup, 0.15 kilograms. The delta T of the cup is going to be that 22 minus 18. So that just comes to 4. And then in the front here, this 9.00 times 10 to the 2, that's the specific heat capacity of aluminum. We can look that up. That's where you get the 900. Similarly, for the water, we can look up the specific heat capacity, and it's 4,186 joules per kilogram per Celsius degree. So these are things that you just look up in the table. You don't have to have them memorized. We have the mass of the water here, and then we have the same change in temperature, 4 degrees Celsius. And then for the unknown, we have its mass, so that's good. And for its change in temperature, again, this is where we have to be careful. We're not doing final minus initial, because final minus initial would have been 22 minus 96. We want to be positive still. So we're going to do the higher temperature, the 96, minus the 22. Or was it 97? 97, sorry about that. Seven minus 22. And so that's what gives us this 75 Celsius degrees for the change in temperature of the unknown rock. So if we divide all of that out, one of the things that we would notice is I would just focus on units within each of those terms to start. So we have kilograms, kilograms cancel out, and also Celsius degrees cancel out within each of these terms, right? We could go to a different color. The kilograms would multiply out, and the Celsius degrees would multiply out. So what we're left with, when all is said and done, is we have joules in this first term and joules in the second term. It's being divided by kilograms and Celsius degrees. So that's how we get to units that we typically have for specific heat capacity, joules per kilogram per Celsius degree. And the number comes out to 1,300 joules per kilogram per Celsius degree. So there we've illustrated how we can use the heat gained is equal to heat lost. We can look at the relative temperature changes to learn something we didn't know, because this goes back to the overall idea that energy must be conserved. So as long as we aren't losing it to the environment, it's got to go somewhere. And we can account for that, which is super cool. We'll see another way that heat can flow in the next section. So I hope you flow right into that.